So let's take a quick look at Chapter 9. Let's do a quick overview. So Chapter 9, we're going to essentially talk about the first three sections, finding the centroid with integration, finding the centroid using the table method, and the theorems of Pappus and Goldinus. I'm not sure why 9.1 and 9.2 aren't switched around in the book because it seems like the table method is easier to integration, but no big deal. The integration is all going to be real super easy stuff, so don't get bent out of shape if your calculus is a little bit rusty. It's going to be pretty easy. So basically, the concept of the centroid is, if you've heard the terms, well, centroid is the center, the geometric center of an object, whether it's a 2D or a 3D object. Uh, if it's a homogeneous, meaning the piece is made up of the same material throughout, the density is the same throughout the body, then the center of gravity, center of mass, and the centroid all come together at the same location. Oh yeah, sometimes depending on the shape of the object, the centroid may not be on the object, which seems a little strange, but it's true. So how do we determine the centroid? So what we're going to do is we're going to pick a differential element. So this differential element is going to be a rectangular element. And then we're going to define the width and we're going to define the area. So we're going to define the width and the length of the area. We're going to need to define it depending upon if we take a horizontal or a vertical in either terms of x or y. So sometimes it's easier, depending on which one it's easier to express it in, it might be easier to pick the horizontal or the vertical axis. I already mentioned that. So you're going to define it, is it dx or dy? You're going to determine, I don't know why they use the squiggly lines. I've always heard x bar and y bar, right? So we're going to define the centroid of the rectangle, and then we're going to integrate that based upon the limits over top of the shape that we're looking at. And again, that's going to be either dx or dy, depending upon which one we picked. Oh, yeah, you can do the same thing for center of gravity, center of mass. Depends if you're using volumes or if you're using areas. So you'll do some examples of homework, do some quizzes, and then ultimately some on the third exam. And every time you do these examples, it'll become self-apparent. So here's a problem that you can take a look at this whole problem in more detail. I've posted it on Canvas in um, the notes for the chapter. Essentially what we have is this steel plate, and we want to find you're ultimately trying to find the reactions at A and at point B. It's an odd shaped plate. You notice the top has kind of a curve to it, and the bottom piece is kind of a triangle piece. So it's not so easy to actually figure out what the weight of the plate is, right? There's no external forces applied. However, there is a weight to this plate. If we could figure out the weight and we could figure out the centroid, right, where that force is being applied, then we could figure out those reactions. So that's essentially what you're doing for this particular problem. So in this case, they decide to pick a vertical strip. So you notice it's very handy when you do one of these problems if you can sketch the strip out, whether you're doing a horizontal or vertical strip. Right, so you need to figure out what the width and the length of that strip happens to be, right? Because you need to find the area. So, right, they're saying here, right, the area is going to be, right, the length times the width. So the width is dx, right? And the length happens to be y squared minus 1. So what they've done is they've taken the y squared and the minus 1 and they've expressed those in x because nicely in the problem they were giving us the equations for those two sides. Right, so they have the dA term in the square root of 2x plus x times dx. Length times width, pretty simple. You need to define the centroid for that rectangle, right? Remember, it's always dead center, so they've called it x in this particular case. Right, we need to express that x. How do we find that x? Well, it's in the center, right? So if you take the distance, the y1 plus y2, and you divide that by 2, that would be the center of the rectangle. However, we're going to, if you notice, we've got a dx term, so we need to express those y's as x's, so we do that. So our y bar term is the square root of 2x minus x divided by 2. So we take and we do our integration, right? Our x bar is going to be the integral of x dA divided by dA, right? So we plug in what we already found for our x bar and for our dA values. You notice the limits go from 0 to 2 because we were sweeping that thing from 0 to 2. So we find the x bar term at 1.257 meters. Right, so we repeat the same process for y bar. Same dA is on the bottom, right? On the top, we're going to have y bar dA. So we have the y bar term, we have the dA term, we plug those values in, and we solve, and we get 0.143. So with that, well, there's the x bar and the y bar for the entire funny shape that we have. So if we place that on the centroid, right, the area is, in this case, given there, so the weight is going to be the density times the area, right, times gravity. So we've got the weight of this thing, right? We apply it at that point that we just calculated as the centroid. And once we do that, of course, we can apply our equations of equilibrium, right? They solve for a moment at A, which allows you to solve for NB. Right, once you have NB and you have the weight, you can solve for AX and AY, and voila, you've got the reaction for that really strange plate. So that's integration. The other way that we can do it is if we have we have some known shapes. So if we have known shapes, we can break our complex piece up into known shapes, and we can find the centroids for each of those shapes and use the table method to find the center of gravity. Now, the one on the left, you notice that there's a hole. So if we have a hole, we're going to use a negative shape in that particular case. So the one over there on the left, you would have a half circle for A, you would have a negative shape for D, you'd have a rectangle for B that has a piece subtracted out. Actually, A is going to have a piece subtracted out of it. Actually, I take that back. So you're going to do A as a half circle, you're going to do B as a rectangle, you're going to do C as a triangle, and then you're going to do the D and subtract that out. Right over on the right-hand side, you've got that big rectangle for A, you've got B and E as triangles, and C and D as separate rectangles. So basically what you're going to do for that one is you're going to divide your whatever the shape is into known shapes. Remember, holes are negative pieces. You're going to make a table where you have the volume or area, depending upon what problem you're doing, along with your x bars and your y bars, and you're going to multiply those together, add those together, and then you're going to use that to find your centroids after you've filled your table in by, right, your x bar value is going to be the sum of the xi a's divided by the a's. Just like the integration, but you're doing it with sums in this particular case. So here's an example. You notice we've got 3 blocks in this case that are put together. I don't know, kind of looks like, I guess it's kind of a cement wall in this particular case. You've got a couple triangles and you've got a rectangle, right? And what do they want us to do? So they want us to, I don't know what to, oh, they just want us to find a centroid. That's all we're doing for this particular case. So hopefully you can see, right, you can break this in, as I just mentioned, into 2 triangles, A and C, and a rectangle B. right? And if we do that, and we start to plug this information into our table, right? We need volumes first. So B, of course, for areas, if you remember, for a rectangle, it's going to be one side times the other, right? For volume, you're going to multiply that by the width, right? And for triangles, right, the area is 1/2 base times height. And again, to convert that to area, we add in the width, and you can see those three are calculated out there for us, right? So we created our table. First column. So first column is our volumes that we just calculated. All right, second column is the X bars for each piece. All right, so if you remember, well, actually, if you don't remember, a real handy thing at this point is to consult the back of your textbook. If you've got a paper textbook, it's right on the back page. You crack open the back cover, and all that information is there. I'm not exactly sure where it is if you're using the e-version, but all this stuff is there. So, right, the X bar for a rectangle, dead center. So is the Y bar, right? So if you remember, for a triangle, right, that centroid is going to be 1/3 of the way from the base up. And it's 1/3 of the way from the big side over, right? So that's how you're going to get your X bars and your Y bars, and your Z's in this case, right, they're all actually rectangles if you look at them from the Z direction. So then you have your X bar times your volume, your Y bar times your volume, your Z bar times your volume. You add those all together in your table. And then last but not least, you take that information and you find your X bar by the sum of the X bar V's divided by the sum of the V's, sum of the Y bar V's, sum of the Z bar V's, all that divided by the V, and you get your location for your X bar, Y bar, Z bar for the original shape. So the last thing in this chapter, 9.3, is the theorems of Pappus and Guldinus. And it may look weird, it may look complicated. Essentially, it's formulaic. So we're going to find a shape that we can spin around an axis to make our shape come up. So when we're finding the areas, we're going to define the surface area. So think of, we got a shape and we want to paint the outside of it. We figure out how far we need to turn it around an axis in radians. Right? We figure out the perpendicular distance that the line is away, and we find out how long the line is. Plug those values in. I have an example that I'll do in another video. For volumes, we're looking at if we cut a piece, if we cut up our shape and we cut it into a piece that we can spin around an axis in that particular case. How far do we have to spin it around the axis? That's the angle, and it's in radians, right? The perpendicular distance is how far the center of that shape is that we're spinning around. And then the A is the area, the size of the area that we're spinning around. Again, we'll do an example of this in another video.